Hi there, and welcome back to the next in my series of Lightboard lectures. This time, rather than focusing on the structure and evolution of jaws, we're going to take a closer look at fish gills, which are the primary structures that they use to exchange gases with the water around them. As a reminder, the enormous surface area of the gills allows fishes to pull oxygen molecules out of the water and to dump their carbon dioxide waste into the water. Just like you, fishes need the oxygen to serve as the final electron receptor in the Krebs cycle, which is the biochemical process that extracts energy from glucose. In short, without oxygen, aerobic respiration can't function, and if you can't respire, you will rapidly expire. In the previous PowerPoint lectures, I've shown you how fishes create the huge surface area needed for gas exchange to occur. And we've discussed some of the ways that fishes move water over the gills, such as ramjet ventilation, tidal respiration, or the most common mechanism, the bucopharyngeal pump. But now I want to talk about what's happening at the microscopic level, the actual gas exchange across the secondary lamellae of the gills. Oxygen and carbon dioxide are both gases, in this case dissolved into water or blood. To understand how the fish pulls oxygen out of the water and expels carbon dioxide into the water, I need to remind you of some of the gas chemistry that you learned in your high school chemistry class or introductory chemistry at your university. And specifically, we need Dalton's law of partial pressures. Okay, there it is, Dalton's law of partial pressures, which states that in a mix of ideal gases, the partial pressure of each gas is the pressure that it would exert if it alone occupied the volume of the mixture. This law has a few very useful implications. For example, it means that we can add the partial pressures of two gases in solution to get the total pressure. In our case, that means P total equals PO2, oxygen, plus PCO2, carbon dioxide. Different mixtures of CO2 and oxygen can have very different partial pressures of those two gases, even if they have the same total pressure. Dalton's law implies that we can find the partial pressure of each gas by understanding the ratio of oxygen to carbon dioxide molecules. For example, if there are lots of oxygen molecules and few CO2 molecules, the partial pressure of oxygen will be high, and the partial pressure of CO2 will be low. And all of this is relevant to fish biology because gases diffuse down partial pressure gradients passively, without any need for energy input. If you put two solutions into contact with each other, one of which has a lot of oxygen and one of which lacks oxygen, the oxygen will flow into the low oxygen solution, without any regard for the pressure of the other gases in solution. This is hugely useful. So let me show you this visually. Dalton's law implies that gases will flow down their partial pressure gradients, from high concentration to low. So this juxtaposition of water and blood at the gills allows the oxygen molecules in green to flow into the blood, and the orange carbon dioxide molecules to leave the blood. All of this occurs passively, without the fish needing to expend energy. That's ideal for the fish, because the whole point of the exercise is to generate energy via respiration. Pretty neat, and rather useful. However, just juxtaposing the blood and water isn't enough to provide for all of the fish's energy needs. That juxtaposition allows diffusion to happen, but the rate at which diffusion proceeds depends strongly on the steepness of the partial pressure gradient for that gas. When the difference in partial pressure is large, diffusion is fast. When the difference is small, diffusion is slow. And when the two solutions have the same partial pressure, diffusion stops. That's a problem. So let me illustrate this problem with a diagram that illustrates what fishes don't do. That will in turn set the stage for a drawing that illustrates their elegant solution to the problem. I'm drawing two parallel lines that represent a single capillary, one of the many that exist in the gills. assume that blood flows left to right through this capillary, as I've marked with the arrows. Above this, I'm drawing another set of parallel lines representing the path that the water takes as it flows through the capillary. In this example, assume that the water flows through the gills in the same direction as does the blood. Now, I'm going to add two numbers to the diagram. These represent the percent saturation of the blood or the water with oxygen. We're ignoring carbon dioxide for now. The 100 means that the water is holding as much oxygen as it can, and the 0 means that the blood is completely deoxygenated. These values tell us about the ratio of oxygen molecules in the two solutions. Lots in the water and none in the blood. As such, oxygen will diffuse rapidly into the bloodstream. So far, so good. But now, let's follow the path of the fluids a little further. As the blood picks up oxygen, its saturation with oxygen increases, while the water's saturation decreases. I'll write a 25 and 75 here, indicating that about 25% of the oxygen has diffused into the bloodstream. At these values, diffusion still proceeds quickly, but not quite as fast as it did at the beginning of the process. Let's move along further. Here I'm writing 40 and 60, showing that about 2/5 of the oxygen has diffused into the bloodstream. And at these values, the partial pressure of oxygen in the two solutions are becoming more similar, and the rate of diffusion slows further. As the fluids continue to flow alongside each other in this example, the oxygen will continue to trickle into the bloodstream, but at a decreasing rate. And that eventually, the blood and the water will reach equilibrium, each with the same partial pressure of oxygen, and the diffusion will stop. I've marked that point here with 50 and 50. One could look at this co-current arrangement as a success. After all, the blood exits the gills half full, and some oxygen for respiration is far better than no oxygen for respiration. But from another perspective, the blood is half empty, and the fish has left a substantial amount of oxygen in the watery environment around it. This arrangement seems inefficient. There has to be a better way. And indeed, there is. So let's look at what fishes actually do. So I've created a similar diagram with the flow of the water on top and the flow of the blood on the bottom. Crucially, in this diagram, the blood and the water will flow in opposite directions rather than the same direction. We call this arrangement countercurrent flow, while the previous was co-current flow. Here, the water is still completely saturated with oxygen as it begins to flow over the gills, and so I'll write 100 here. And the blood is still completely deoxygenated as it enters the capillaries, and so I'll mark that with a 0 here. Let me now add a bunch of other numbers, showing the percent saturation of the blood and water with oxygen at different points along the flow. Remember that these are proportional to the partial pressures of oxygen in each solution. So at every step along the way, the blood is juxtaposed with water that has a higher partial pressure of oxygen. Where the blood enters the capillary, it encounters water leaving the gills that has already given away most of its oxygen. But some is more than none, and so oxygen flows into the blood. When the blood is about to leave the capillary, it encounters water just entering the gills, and that water has all the oxygen that it can hold. Complete saturation means higher partial pressure than almost complete saturation, and so here as well, the oxygen flows into the blood from the water. This countercurrent arrangement sets things up so that oxygen diffuses into the bloodstream at every stage of the blood's passage through the capillary. Crucially, it extracts all of the oxygen from the water that passes through the gills, leaving essentially none behind. This design is efficient and elegant and crucial. It's also true. And as I'll show you with an illustration in the next lecture, if you dissect the microstructure of fish gills, blood flows from posterior to anterior in the capillaries of the secondary lamellae, while water flows anterior to posterior, in through the mouth and out through the operculum. Overall, oxygen holds too much importance for a fish to waste the opportunity to seize all that it can. So they have evolved the solution of countercurrent flow. To do otherwise would have been illogical. Now you may also be wondering about carbon dioxide. How does the fish get rid of it? Well, countercurrent exchange to the rescue again. Carbon dioxide diffuses out of the bloodstream into the water simultaneously with the diffusion of the oxygen from the water into the blood. Remember that each gas obeys its own partial pressure gradient, and so each can and does diffuse in opposite directions. If you're paying close attention to these numbers, you might also be wondering about the rate at which this process unfolds. The saturation values that I've juxtaposed in this diagram are almost equal at each stage of the blood's passage through the capillaries. Countercurrent flow thereby implies that the partial pressure gradients are much less steep than at the onset of co-current flow. Doesn't that slow down diffusion? Indeed, it does. The length of the capillary and its large surface area help to solve that problem, essentially giving diffusion more time and opportunity to proceed. But the complete solution also involves an almost miraculous molecule called hemoglobin, which greatly accelerates the process. We'll explore hemoglobin's action in the next lecture. For now, I think I'll let the torrent of information trickle out and let you breathe a little easier. Thanks for going with my flow. And if you think that my puns are a gas and your enthusiasm is bubbling up, I'd love to catch wind of it. Best fishes.